Hello, everybody. Welcome to this first episode of our webinar, whose title, as you can see here, is Functional Coatings at the Forefront of Surface Technology. My name is Marco Gulli, and I'm Italian. I have been working as a sales and technical consultant at Optitune since March 2024. In this first episode of our webinar, we are going to introduce some novel surfaces and innovative materials. In particular, we will be talking about aspects that relate with aesthetics, performance, and sustainability of such innovative materials. Let's first have a word about our company. Optitune Oy is a Finnish company based in Oulu. It was founded in 2003, and its main focuses on R&D activities and chemicals production. We have held and nurtured a wide network of collaborations with research and academic institutions, both at a national and international level. For example, in Finland, we work with VTT. Our company is based on a team of committed and skillful chemists who have envisaged, tailored, and industrialized a wide range of coatings whose primary purposes are to make surfaces more durable and materials more performant. We are specifically producers of chemical formulations, which are solvent-based, and they allow to protect materials against degradation, which can naturally happen over time due to environmental exposure and aging factors. For example, we can enhance optical properties of certain materials like optoelectronics devices, as you can see here, and we are able to provide a wide range of surfaces with anti-fingerprint, easy to clean, abrasion resistant, hydrophobic, and oleophobic features. Optitune has been certified as compliant to ISO 9001 and ISO 14001 by DNV, the Norske Veritas, since 2016. And we are voluntary signatories of Agenda 2030 for goal number 7, which relates to affordable and clean energy, and goal number 12, which is strictly linked with responsible production in terms also of reduction of waste, which has been particularly massive for electronic devices recently. Our portfolio of coatings has a wide range of applications. It's really versatile. As a matter of fact, we can work with the metal and glass surfaces, usually common in many kitchen and home appliances, which are daily exposed to intensive usage. So making them more durable and performant is key in order as well to reduce waste production. We have matured a good expertise with plastic coatings as well to be applied to screens. And we have a good degree of know-how with light management and optoelectronics. Currently, one of our focuses is, of course, on doing extensive research to devise solutions with the lowest environmental impact possible. As I just said, the applications of our coatings are varied. We can work with conductive and non-conductive surfaces, and we have recently experimented with PVD-coated items as well. And we observed that they can actually provide really suitable interfaces for our nanocoatings. So we are able as well to make PVD manufacture more performant in terms of easiness to clean, anti-fingerprint properties, abrasion resistant, hydrophobicity, and oleophobicity. PVD here stands for physical vapor deposition. It's an acronym. The first historical example of PVD dates back to 1857, when Michael Faraday evaporated metal wires under vacuum to obtain 2D films. Actually, after that date, there were many important developments in many branches of physics, like electromagnetism, and later on quantum mechanics and relativity, which were crucial to explain some mechanisms behind plasma, which by the way, is a really important part of PVD processes. In the second half of last century, there was an increase in demand from markets to produce the decorative and functional coatings to a wide range of applications and manufacturers. So there was a soaring popularity of wet bath technologies, like, for example, electroplating. But soon it became evident that these techniques are associated with drawbacks like high energy consumption, and they can release easily some hazardous substances in the environment, so they are not really sustainable, and they can expose workers' health to significant risks too. So in the 80s, there were the first important investments to industrialize dry coating technologies, and among those, PVD technologies were a very good candidate. And from these efforts, it emerged that tin coatings were successfully applied for tool making processes in order to replace as well less clean and less cost-effective alternatives, like, for example, wet bath technologies. In this period, so in the 80s, there was an increasing interest from the academia as well towards PVD. Many researchers made predictions about, for example, as we can see here, the number of publications on PVD per year over time. And they predicted that from 2000 on, there should be an increase of popularity of these technologies. And also, they predicted that the Asia-Pacific PVD market, for example, would see an increasing popularity in let's say, in this period, so in very recent periods. And the reason for them to hypothesize these changes was also, for example, in the increase of gold prices, which happened in this period, so in the 80s. And this drove, for example, the high fashion industry to look for alternatives to replace traditional coatings or, let's say, traditional industrial processes with PVD. PVD technologies soon were able to produce three different kinds of coatings, decorative coatings, in which the aesthetics is really, really important in terms of color and brightness, for example. Deco-functional coatings, which is exactly our focus in this webinar. And in this case, they should combine both, let's say, aesthetical appealing effects with performances. And there was a significant increasing popularity with, let's say, applications more in fields like semiconductors and automotive, so more like technical fields. And speaking about PVD, it can actually, in some cases, and in the case of deco-functional coatings, it can increase some properties, it can improve some properties of steel surfaces, for example. There are few PVD coatings which can increase the surface hardness of steel, for example, and they can improve chemical resistance to salty atmospheres as well. Of course, in terms of aesthetics, there are a few, let's say, systems of coordinates like the Scilab parameters, LAB, which allow for a specific and more precise measurement of color. And most of PVD technologies which are commonly available on the market allow for producing a wide range of colors and hues. PVD technologies usually come with many advantages with respect to wet bath technologies. They are fully REACH compliant. They involve a lower energy consumption. It's easier to obtain biocompatible coatings, also for food contact, for example, and it is the case of cutlery. And they come with an increased workplace safety. As a matter of fact, they do not involve generally the production of hazardous chemicals and their release in their environment. Let's say that PVD technologies, on the other hand, allow for producing a wide range of coatings. That's true. These can come with a few limitations. Some PVD coatings indeed come with high energy surfaces, which means that they can be easily printed by fingers, and they may not be easily cleaned. Also, some chemical mixtures behind PVD coatings can be, let's say, sensitive to some cleaning products commonly used in the household, like the case of chromium with bleach. And other PVD coatings may have low abrasion resistance. So our solution to overcome these drawbacks is to boost these, let's say, these performances of PVD coatings and PVD manufacts by combining them with our nano coatings. And this is exactly what we mean here by novel surfaces. In the next episode, we will be talking about PVD surface treatments more in detail. We will be tackling some aspects that relate to substrate requirements, pros and cons, technologies, applications, and the potential and limits of PVD technologies. I truly thank you for your attention, and I will be waiting for you in the next episode.